So we're going to talk about bar charts, LOL diagrams as we call them. You get it? Oh, anyway, so you're going to make a bar chart for the initial situation. So usually when we're keeping track of energy, there's something going on. So it might be a collision, it might be some motion, something's happening. So you're going to pick an initial situation and you're going to list the types of energy involved in the situation on the horizontal axes here, and then draw bars representing how much of each energy there is. You're going to have a circle. The circle is going to represent the system, and you will list the things that are in your system in the circle. And then you'll have your final situation where you think about the energy that's there in the final situation, and you draw the bars. So it's very important to make sure that the total blocks of energy that you have in the initial situation is equal to the final situation. So if you have 4 blocks of energy here, you need to have 4 blocks of energy here. And then you're going to write the energy equation. In the energy equation, we know that we are following the law of conservation of energy. So our energy equation is just going to be all of the initial energy added together equals all the final energies added together. Remember, energy is a vector. I mean a scalar. Goodness, energy is a scalar. So initial energy equals final energy. So you'll take all the energies here, add them up, equals all the energies here, add them up. Okay, let's give some examples. It's the best way to do this. So let's say that we have a person bungee jumping, and they are starting up here. There's a slack bungee. I don't know what happened to their leg. It used to be going up this way. And here they're moving a little bit. Here they move faster. Here they move faster, but they get lower. At this point, the bungee is all the way stretched out, and they're not moving. That's what that dot represents. And so we want to look at the energy at this situation 1 and this situation 2. Now, we're going to establish our system. So we're going to put the person in the system. We're going to put the earth in the system. You have to have the earth in the system if you are working with gravitational potential energy. So if the object's position in the gravitational field is changing, you must put the earth in the system. Another thing you have to do is establish a 0 reference line. So that's supposed to be horizontal, but we'll just pretend it is. So this is a 0 reference line. This is where I'm saying there's 0 gravitational potential energy. Really, only changes in gravitational potential energy matter. You might say that you have 0 gravitational potential energy because you're sitting on the floor right now. Well, what if your floor caved in and you fell into the basement? You gained kinetic energy as you fell. Where did that kinetic energy come from? It came from gravitational potential energy. So you may feel like you have 0 because you're on the floor, but you could still go down and gain kinetic energy. It just has to do with gravitational potential energy has to do with your position in the gravitational field. So changes in that position are what we care about. So we draw a 0 reference line to show where the gravitational potential energy is 0. Now we're looking at positions 1 and 2. At position 1, the person has some gravitational potential energy. The symbol is U sub G. U just means potential, and then the G is gravitational. So a gravitation. The U is potential energy. And it's moving, so there's some kinetic energy. And we're going to neglect air resistance and stuff like that, so that's it. At the end, there's no kinetic energy and there's no gravitational potential energy, but now the bungee cord is all stretched out, so there's some elastic potential energy. So it's a U sub E, or EL is what I usually put for some reason. So let's say that we have 2 blocks. Oh my goodness, that was very bad. Let's try that again. Okay, so we have 2 blocks. I gotta get oriented here. 2 blocks of gravitational potential energy, 2 blocks of kinetic energy, and then at the end there's no kinetic, no gravitational potential. It's all elastic potential. So we have 4 blocks of elastic potential energy. So we're showing that our energy is conserved here. And then we just write out all of our initial energies, so gravitational potential plus kinetic equal all of our finals, elastic potential. And there's our equation that we could use. Once we have equations for all these, we can plug things in and solve for this. Let's do another one. Here's a rocket taking off, and this rocket is here, it's not moving, it's on the ground. So I'm going to choose this as my 0 reference line, the ground. And then here it's moving and it's gotten higher, here it's moving and it's gotten higher. So where is that energy coming from when it takes off and it's going higher, that is chemical potential energy. So you have to deal with chemical potential energy conceptually, but not mathematically. So we start off with chemical potential energy. That's all we've got. Here we have still some chemical potential energy because we're not out of fuel yet. We have some gravitational potential energy. We have some kinetic energy, and we also have some dissipated energy. So we're going to put E-dis for that. And my chemical is a little too big there. Let's see if I can move that over so that we have some room. Okay. So now we're going to think about, oh, I didn't do my system. Sorry. We're going to have the shuttle, the space shuttle, and the fuel, and the Earth. Oh my. I was distracted by the fact that fuel looks like full, but that's okay. You know what I mean? And then at the end here, we still have chemical potential energy, we have gravitational potential energy, we have kinetic energy, and we have dissipated energy. So we start off with a bunch of chemical potential energy. I'm going to do 4 blocks, but this is going to split into too many things, so I'm going to do 8 here. And then we are going to see that some of our chemical potential energy is gone. It's turned into gravitational potential energy and kinetic energy and dissipated energy. So I'm going to say we have half a block of gravitational potential, half a block or 1 block of kinetic, and 1 block of E-dis. And so we still have 8 blocks. 1, 2, 3, 4, oops. 1, 2, 3, 4, 5, 6, 7. Oh, did I screw that up? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I definitely screwed that up. I'm breaking the law of conservation of energy. Okay. Now, this has 5. 1, 2, 3, 4, 5, 6, 7, 8. So we're still at 8. In this second one, you can just go like this for the same system. And then here, our chemical potential energy would have dropped more. So maybe we're down to 2 chemical potential energies, 2 gravitational potentials, 2 kinetics, and 2 dissipated. This is purely qualitative, so you don't have to worry about exactly how many blocks you have. The important part is that you've got the same number here as you have here as you have here. Now we write our equation. So we have chemical potential energy at position 1 is equal to chemical potential energy at 2 plus gravitational at 2 plus kinetic at 2 plus dissipated at 2. And that's equal to chemical at 3 plus gravitational at 3 plus kinetic at 3 plus E-dis at 3. There we go. Okay, we have another one here. I think I'm just going to do a couple of them. So we have the one here, and then let's do this one, and then let's do this one. So we're going to take out 2. Okay, so we're going to put the person jumping on the trampoline. So person, the trampoline, and the Earth in the system. We have to have the Earth in the system because the position in the gravitational field is changing. I'm going to choose this lowest position of the person as my 0 reference line. So that's where the gravitational potential energy is 0. So in the beginning here, I have this person, and they're like at the bottom of their jump on a trampoline. So they're not moving, which is what that dot represents, and they're at the 0 reference line. So we have all elastic potential energy. Then at position 3, they are up in the air a little bit and they're moving. There's no more elastic potential energy because the trampoline is not stretched at all. So they have some gravitational and they have some kinetic. I'm going to say they have 2 of each. Doesn't really matter. You just have to make their gravitational get bigger each time. So for 4, they're not moving. They're at the top of their height of their jump. They're about to come back down. So all we have is gravitational potential. It's all gravitational potential. And then we could write our equation. Elastic potential energy at 1 is equal to gravitational at 3 plus kinetic at 3, which is equal to gravitational at 4. And there's our energy equation. Okay, let's make this a little bit more complicated. Now let's talk about a bar chart for an open system. So for an open system, energy, before we did a closed system, so energy was not entering or leaving the system, but now we're going to have an open system. So all of this stuff is the same. You still put your system, you list your things in your system, in your circle, but this time we're going to draw an arrow going into or coming out of the circle to show energy coming into the system or leaving the system. The tail of that arrow is going to the tail of the arrow is going to be made up of boxes. Use purple so we don't, okay. And those boxes are just like your blocks. So you have your arrow like this. So if we were doing positive work, our arrow would go in, and then we might have 1, 2, maybe 2 blocks of energy going in. Or you might have an arrow coming out like this, and you might have 3 blocks of energy coming out. And then when you write when you're making sure you have the right number of blocks, you should have this number of blocks plus or minus these number of blocks equals this number of blocks. And so when you write your equation, you should get your initial energy plus or minus work. Oops, that's not what I tried to write. Okay, initial energy plus or minus work, depending on if it's coming into or leaving the system, equals final energy. So let's do an example. I didn't put the LOL diagram on here. Let me really quickly get this LOL diagram. All right. Okay, so let's say that we have this car, and this car is traveling to the right. There's a force on it to the left. So a little bit later, let's say the car comes to a stop. Okay, so this is situation 1, this is situation 2, and that force on it is causing it to come to a stop. So if I put just the cart in the system, and the cart's all that I need to have in the system, I don't need the Earth because it's not changing its position in the gravitational field. So we put the cart in the system, and we start off and we have kinetic energy. My goodness, that's quite slanted. And then in the end, we don't have any energy at all. There's no energy left. And so I must have energy leaving my system, and there must be 3 blocks leaving. So I have 3 minus 3 equals 0. So I get kinetic energy minus the work equals 0. You could also always add the work and then just plug in a negative value. Either way is fine. So that's how you would do that. You might have, you could do another one with like the force pushing it in the same direction and it would speed it up. So you'd have energy entering the system. But that's conceptually how you're going to set up these problems or these situations. And this is going to be the base for all of the problems that you do. So you're always going to start with this. You're going to start with an LOL diagram. And then you're going to use your LOL diagram to make your equation, this equation right here. And then next week or soon, depending on when you're watching this video, we are going to, that's not much better, we are going to derive equations for each of these terms, and then you'll be able to plug things in and solve. All right, nice work. That's it.